NASA has funded 8 advanced technology concepts that agency officials believe could help transform space science and exploration. The high-risk, high-reward ideas which received grants under Phase 2 of the NASA Innovative Advanced Concepts (NIAC) program include a possible way to induce a hibernation-like state in Mars-bound astronauts and a proposal to blast tiny spacecraft between the stars using powerful lasers. The NIAC program is one of the ways NASA engages the U.S. scientific and engineering communities, including agency civil servants, by challenging them to come up with some of the most visionary aerospace concepts. Steve Yurchik, Associate Administrator of NASA's Space Technology Mission Directorate in Washington, D.C., said in a statement Friday, May 13. This year's Phase 2 fellows have clearly met this challenge. Gallery, Visions of Interstellar Starship Travel Phase 2 NIAC awardees receive up to $500,000 for 2 years of work. The goal is to further develop ideas that have already been fleshed out with the aid of a $100,000 Phase 1 NIAC grant, which supports initial analysis studies. Here are the 2016 NIAC Phase 2 concepts, along with the principal investigators for each: Advancing Torpor-Inducing Transfer Habitats for Human Stasis to Mars, John Bradford, SpaceWorks, Inc. in Atlanta. Bradford and his team are working on a way to put astronauts in a sort of hibernation, by lowering their core temperatures significantly. This strategy could make the long trip to Mars cheaper, safer, and less taxing physically and psychologically for crew members, the scientists say. Directed Energy Interstellar Study, Philip Lubin, University of California, Santa Barbara. This project's investigators aim to develop an interstellar spaceflight system that would accelerate sail-equipped probes to incredible speeds using powerful laser blasts. This basic idea is at the heart of the $100 million Breakthrough Starshot project, which Stephen Hawking and other scientists announced last month. Magneto-shell aerocapture for manned missions and planetary deep space orbiters, David Kirtley, MSNW, LLC in Redmond, Washington. In this concept, a spacecraft would slow down upon approach to a planet by generating its own magnetic field. This field would trap ions, which would then be dragged through the planet's atmosphere, decelerating the probe. Magneto-shell aerocapture could conceivably allow missions to dispense with thermal protection gear, thereby saving lots of money, its developers said. Cryogenic selective surfaces, Robert Youngquist, Kennedy Space Center in Florida. Youngquist and his team have developed a highly reflective coating called solar white that, the scientists said, could enable long-term cryogenic fuel storage, superconductor operation in deep space and other advances. Experimental demonstration and system analysis for plasmonic force propulsion, Joshua Rovey, University of Missouri in Rolla. The researchers involved in this proposal aim to demonstrate the feasibility and benefits of plasmonic force propulsion, which would take advantage of the interaction between sunlight and asymmetric nanostructures on a tiny spacecraft to move that spacecraft around cheaply, efficiently, and precisely. This novel type of propulsion could open up new space exploration possibilities for small spacecraft, Rovey and his colleagues said. Flight demonstration of novel atmospheric satellite concept, William Engblom, Embry-Riddle Aeronautical University in Daytona Beach, Florida. The idea here is to connect two uncrewed, glider-like aircraft using a long, strong cable. This system could stay aloft high in Earth's atmosphere pretty much indefinitely, using only wind and solar energy, Engblom and his colleagues said. Further development of Aperture, a precise extremely large reflective telescope using reconfigurable elements, Melville Ulmer, Northwestern University in Evanston, Illinois. Aperture is a space telescope concept that would boast an extremely large, membrane-like primary mirror, whose shape would be corrected after deployment in space. Tensegrity approaches to in-space construction of a 1-gram growable habitat, Robert Skelton, Texas Engineering Experiment Station in La Jolla, California. This project's originators aim to show how a ring-shaped, rotating human habitat could feasibly be built in space and how that structure could grow, to accommodate more and more visitors, or inhabitants. Phase 2 decisions are always challenging, but we were especially challenged this year with so many successful Phase 1 studies applying to move forward with their cutting-edge technologies, Jason Derleth, the NIAC program executive at NASA headquarters in Washington, D.C., said in the same statement. Whether it's tensegrity habitats in space, new ways to get humans to Mars, delicate photonic propulsion, or any one of the other amazing Phase 2 studies NIAC is funding, I'm thrilled to welcome these innovations and their innovators back to the program, Derleth added. Hopefully, they will all go on to do what NIAC does best: change the possible.